2/7. So the effect of throwing the absolute value on the outside of the series in the way that we have just done is just force the thing that it converges to be positive. So nothing really earth-shattering. In fact, we just really copied a lot of our previous work. Any questions with part B then? Okay, part C is really the new thing. In part C, we're putting absolute values into the nth term. So this is what it would look like next. So in part C, we investigate what happens as n goes from 1 to infinity of the absolute value of the nth term. It feels like part B, but that change that we made is subtle but really hugely important, because now we can write that this is equal to the summation as n goes from 1 to infinity of the absolute value of -2/5 to the power n. So that's what the absolute value of the nth term would look like in the series. There's lots of things that are happening here. When n is even, for example, when n takes the value of 2, 4, 6, 8, this is all going to be squared, so the negative doesn't matter. But when n is odd, we'd be cubing things. For example, when n is 3 or 5th power, the whole result is going to come out negative, and absolute values is going to kill it off immediately. So we can say that this is now just the summation as n goes from 1 to infinity of 2/5 to the power n. So that is a different change. We now have a different common ratio. It's still a geometric series. This time the common ratio is r equals 2/5. It's less than 1, so it converges. And we still have a is equal to 2/5, which will produce when we put it in the proper form. So this still converges, but it won't converge to -2/7 any longer because we now have only positive terms. Let's find out what it converges to next. Any questions so far with our work on part C? Okay, so we can say, very next, we need to have n-1 here, so we do one little trick with exponents to write this as 2/5, and that's our a, times 2/5 to the power of n-1. Then this sums to a divided by 1 minus r, like before. And from here on out, it's really just a matter of cranking out all the arithmetic. A is 2/5. In this problem, it's 1 minus 2/5 again for r. So this will turn into 2/5. This is 5/5 minus 2/5, so we get 3/5. So it's 2/3 altogether. So we went from -2/7, but if we throw the absolute value on the nth term, making all of the terms positive in the series, we came out with a 2/3. Any questions with that so far? Okay, so the major idea with absolute convergence is that if we're trying to test a series from convergence or divergence, and some of the terms are negative, but it doesn't alternate, or possibly all of the terms are negative, then we just need a new test. And this is our new test. Well, we can call this, say, a theorem. The theorem says if a series is absolutely convergent, then the series converges. In other words, absolute convergence implies ordinary convergence as we've defined before. And there's an optional section in the reading in section 11.6 about rearrangements, which discusses a little bit more why absolute convergence is more powerful than ordinary convergence and the things it does for us. But that's our theorem. It tells us then if we want to test a series from convergence or divergence, and we're not too keen on dealing with the negative signs, we can just take the absolute value of the nth term and analyze it from then on. And in this series that we've looked at so far, we can say that this is absolutely convergent since the summation as n goes from 1 to infinity of the absolute value of an converges. So that theorem is maybe not good for a whole lot in this problem because we knew from part A that it converged already. But let's go then next to a problem where the part A, where we're trying to determine whether this converges or not, may not be completely straightforward, and we really would like to have a new test. But any questions so far? Okay, so the first series of the day was absolutely convergent, just because this converged. So now let's go off to a new set of series, a new series where we'll simply test for convergence, divergence. So instructions on this is back to the familiar test the series for convergence or divergence. And the first one we'll look at is, let's let it be the summation as n goes from 1 to infinity of sine n divided by n cubed. So that's going to be our series. And once again, we want to determine whether it converges or diverges. We need to classify the type of series it is. We do have a sine n, and we've seen things like cosine n pi that gave us something that was alternating between positive 1 and negative 1. However, if we take a look at sine n, the curve for sine n will look about like this. But we only are looking at discrete points on this curve, not everything. And if we go up to, say, this is 0 and this is pi, so this is about 3 roughly, we can call this 1, 2, 3. It really has values that starts off positive for 3 in a row. Then we're going to have values that are negative, either twice in a row, 3 times in a row, and so on. So even though it goes positive and then goes negative, it's not strictly alternating. Alternating has to bounce between positive and negative on every consecutive term. So this is kind of a messed up series, but that's okay. It is comparable to a p-series if only the sine n were gone. And that's where our new test can work for us. But any questions so far? Okay, so the test we're going to use is, we will use the absolute convergence test. In other words, we're just trying to use this theorem here. And the test for absolute convergence, it says if a series is absolutely convergent, that means that converges. So if we want to apply the absolute convergence test, our very first step is to take the absolute value of the nth term and see what happens. But let me add just a little bit to this problem. Let's call this the sum as n goes from 1 to infinity, a sub n. That way we don't have to rewrite the entire series every time we refer to it. We'll just use that as an effective variable. So now we're going to consider the summation as n goes from 1 to infinity, the absolute value of a sub n. That's the summation as n goes from 1 to infinity of absolute value sine n divided by, well, n cubed could be positive or negative, but the index n starts at 1 and only takes positive values. So the absolute value of n cubed is just n cubed. We could put it in if you like, but it simplifies to that, which is slightly nicer to work with. Any questions to that step? Okay, so right now we're trying to analyze a series that looks like this. If we find out that it converges, it would be absolutely convergent, then the theorem would say the original series is convergent as well. So that's the logic so far. And to do that, we just have to work out something with sine n in absolute value. Anyone see what we could do with sine n in absolute value? It's kind of the crux of the problem, right? Because as it stands, this looks worse than what we started with, sine n. We threw an absolute value symbol on it. But the reason for doing that is the graph for the sine curve has maximal height at 1. This is a horrible graph. Minimal height at -1, so use your imagination on that graph. And what that implies for the sine curve is that sine x in absolute value is always less than 1 or equal to it, and always bigger than or equal to 0. And that will also hold if we look at the absolute value of sine n, where n is just an integer. They'll still be bigger than or equal to 0, less than or equal to 1. So whenever we have trig functions, not always, but in this case when it's just sine n, that's always a wonderful estimate to have at the ready. What it is going to allow us to do is take a sub n, which is defined to be sine n in absolute value, divide by n cubed, and we can say immediately that it's less than or equal to 1 by this estimate, divide by n cubed. So that's what I would write so far. If we wrote something that looks like this using that estimate, what kind of a test are we trying to use now at this stage? Yeah, we're trying to use the comparison test, compare this to something that's just easier to work with, and that'll be a series whose nth term is 1 over n cubed. So we can now say compare the summation as n goes from 1 to infinity, the absolute value of a sub n, to the summation as n goes from 1 to infinity, 1 over b sub n. Again, writing all this out is not strictly required, but it's a good habit because we have to refer to lots of different things when we navigate all these tests. So in the comparison test, I'm comparing to this one, which is the sum as n goes from 1 to infinity of 1 over n cubed. So that's the thing we'll compare it to. But if we use a comparison test, we have to also test this new series for convergence and divergence. This is not too bad. What kind of a series is this one? Right, here we have a p-series. This is essentially naming the test we're about to use. It converges, and the reason for the convergence is the p in the p-series is 3, which is greater than 1. So that's the conclusion, that's all of the work, and we indicated what kind of series and test was used. Okay, so now we start working backwards. We just compared this series to a known convergence series, and we also know that this known convergence series has terms that are always larger. So the series here that we'd like to compare it to must also converge as well. Does that make sense so far? Okay, so then we can say, so the sum as n goes from 1 to infinity of a sub n converges by the comparison test. This is kind of a weird problem because it's almost as if we're writing more words than we are actually doing math. There's a lot of copying and notation, but we haven't really done a lot of math on this. We're just invoking theorem after theorem to run through it. So far this is where we're at. We know that this converged because we used a comparison test comparing to a known convergent p-series. But if this converges, the very next theorem says if a series is absolutely convergent, then the original series converges. So now we know this shows that the summation as n goes from 1 to infinity of a sub n is absolutely convergent. And really, if you left it at that stage, that would be okay, because we'll get to the point where we think of absolute convergence as a stronger version of regular convergence, which it is. But this theorem is telling us, if you just called something as absolutely convergent, then it really is convergent. So I mean, it's a good thing to actually say explicitly at least once. So let's add maybe one more. Therefore, the summation as n goes from 1 to infinity of a sub n, that thing over there, sine n divided by n cubed, converges. This is really just to be complete. If you left it at absolutely convergent, again, that should imply convergence, and the book does prove it as well. But any questions about this so far? So this is a great test because something like sine n divided by n cubed, this is not something we can handle by anything. Not even the integral test could handle this because the series doesn't involve strictly positive terms. It's not an alternating series, and the test for divergence fails. So it's not a p-series, it's not a geometric series, and it would be very hard to find something to compare it to, unless we took this as an estimate. So this is probably one of the first series that we've looked at where we really, really needed a new idea to get through it. Any questions about it? I guess I have one more question about this. How many tests did we actually use in total on this problem? We used the absolute convergence test. We just indicated that at the very start. So how many tests total did we actually use? Yeah, we used the convergence test, the p-series test, so we're up to 2, and there is something else, the comparison test. So some of these problems, you can possibly use several tests in one go. That's kind of weird, but that's also why we have to study the test extensively to see how they coexist with each other. Any questions with this problem so far?
Yeah.
Yeah.
Will it follow the flow chart then as we do these tests?
These two tests right here?
Yeah, like we're following the flow chart and it pushes down.
Not necessarily, because remember, one flaw in that flow chart is it does not have this theorem right here. If a series is absolutely convergent, then it converges. So that's the one thing that's missing. It'd be nice to have it on there, but you can't fit everything. They must have studied out of a different book, the folks that produced it. But also, I need to personally study that flow chart. It's not something I use too much personally. Well, other questions so far? Yeah?
So a series can converge, but it can't be absolutely convergent?
That is correct, yes. That is very strange.
Can you show us something that we like?
Yeah, absolutely. Let's also go to a new definition since you mentioned that, and we'll do a couple more examples along those lines. That's the reason that we said it's absolutely convergent. We also said it converges, which is redundant, but there's a reason for that redundancy. And the reason is we really have a trichotomy with series. A series can either converge, it can converge absolutely, or it can converge conditionally. So we want to investigate the 3 ways that things can either, 2 ways to converge, 1 way to diverge, and that's our new definition. So let's let the summation as n goes from 1 to infinity, a sub n, be any series. Let's say be a series that converges so we have to start with a known convergent series. Then we'll add a little bit more. If the summation as n goes from 1 to infinity of a sub n diverges. Well, first let's pause right here. We just said that the nth term in absolute value, this is a series, diverges. That means we are not absolutely convergent. But it did converge because that's what we assumed on the get-go, the very start. So we're going to say the series converges, this series diverges, in other words, it's not absolutely convergent. Then the series n goes from 1 to infinity a sub n is said to be conditionally, use yellow, convergent. So let's look at some examples of conditionally convergent stuff, because those are definitely really, really weird. Anyone happen to know an example on the offhand? Okay, let's start with that then. The prototypical example of something that's conditionally convergent. So for this problem, we'll say, show that the alternating harmonic series is conditionally convergent. Okay, so this is our problem. It's a bit of a vocabulary problem on the onset, because here we have to say what the series actually is. So we'll start with defining our own series. It'll be the summation as n goes from 1 to infinity of a sub n, which is the summation as n goes from 1 to infinity of something how does the alternating harmonic series look like then? Anyone happen to know its definition for the nth term? I'll start. It's alternating, so it's got to have this thing, right? So that's got to be there. Some people might put an n minus 1 or an n plus 1. We usually just go with the n in this book. What's the other half of it? Yeah, exactly. So negative 1 divided by n is the alternating harmonic series. So we want to show that it's conditionally convergent. And in our definition for conditional convergence, we have to first show that it's not absolutely convergent. In other words, if we throw an absolute value in the nth term, we need to show that that diverges. So that's our step 1. So for this set of instructions, if you're told to show something is conditionally convergent, and that could be an exam problem, I'd actually give you this series if it were an exam problem, there's a sequence of steps that we have to take. And step 1 could be to show this thing, the series whose nth term has the absolute value applied to it, is divergent. So let's do that as our first step. We have the summation as n goes from 1 to infinity. Absolute value of the nth term, a sub n, is equal to the summation as n goes from 1 to infinity. The absolute value of the nth term is just going to wipe out to negative 1 to the power of n. Then n of the denominator is always positive, so it turns into 1 over n. But then 1 over n is the harmonic series, which is a known divergent series, or the divergent p series with p is equal to 1. So we can say here, this is the divergent harmonic series. So whenever you encounter this series here, you don't really have to say much. You don't have to test it. You just can say what it is and what it does. It is the harmonic series, and what it does is it diverges, and that would be just fine. So that's our step 1. We know that this does not converge absolutely. So the summation, as n goes from 1 to infinity of a sub n, is not absolutely convergent. Because we throw an absolute value in all the terms, and we have the harmonic series which diverges. Step 2 is to show that this, in fact, converges. But we've done that before. It converges by the alternating series test. So step 2 is to show that the summation of a sub n without absolute values converges, or is convergent to maintain parallelism. But once again, once we look at that, in our particular problem, there's not a lot to do, so I'll do a more exciting one very next. The summation as n goes from 1 to infinity of a sub n is negative 1 to the power of n divided by n, and this is the convergent alternating harmonic series. So that's another one. Those are the big two that are just known to diverge if it's the harmonic, and known to converge if it's the alternating harmonic series. So there's no test needed on those two. Step 3 is just the conclusion. I mean, it's an important step. In step 3, we can say the summation as n goes from 1 to infinity of negative 1 to the power of n divided by n is conditionally convergent by this work. Since we know it converges, but it does not converge absolutely. And there's some serious ramifications for a series that's conditionally convergent. Those are definitely the odd ones out, and there's some problems that they cause. The book highlights a little bit of it with their subsection called rearrangement. It is an optional subsection in 11.6, but it's a decent one to read to get a feel for why we care about absolute convergence. But any questions so far with that particular problem? Yeah.
So is there any way a series can converge, but it can't converge conditionally or absolutely?
It turns out that can't happen.
Okay.
Which is good, right? There's no crazy side cases. Once we've defined absolute convergence and conditional convergence, we really have everything. And that's our final theorem so far before we look at the ratio of the root tests. That theorem says, let's write it as a theorem. It says first, let the summation as n goes from 1 to infinity, a sub n, be any series. Then 1 and only one of the following outcomes will occur. So we have a trichotomy, just one and only one of three things can happen, and one of the three things must happen. The first is, for part 1, it is absolutely convergent. I'll write CONV for convergent since I'm running out of space. The second thing that can happen is this weird case. The alternating harmonic series is definitely a very weird series. Things can converge conditionally. And the third case is it might diverge. And we only have one working notion for divergence. If it diverges, then the limit of partial sums did not exist. So that's good to know that there is a flavor of divergence. We only have one notion, but we do have two notions of convergence because weird things can possibly happen to a convergent series. If a series is absolutely convergent, then those are the ones that we really like. Not too many surprises can happen with those. But any questions so far with our last theorem? Okay, let's maybe try one more like the last problem with maybe a harder set of stuff. We want to show that the following is conditionally convergent. Show that the sum of n as n goes from 1 to infinity, which is defined to be, let's see here, we should do an exciting one. How about -1 to the power of n divided by n square root of the natural log of n, show that this thing is conditionally convergent. Okay, so that's our new problem. Really, we're just going to redo steps 1 and 2. Well, you could do step 2 if you'd like first. They can be done in any order. First thing, maybe let's take the absolute value of everything because that is the new technique in this section. So we'll look at n goes from 1 to infinity, the absolute value of a sub n. This is the summation as n goes from 1 to infinity of the absolute value of -1 to the power of n divided by n square root of the natural logarithm of n. So we have to determine what happens with this. We're expecting divergence because we're told from the problem to show something is conditionally convergent. So if I take the absolute value of all the terms, we'll get the following, and we're expecting that this ought to diverge. 1 over n square root, the natural logarithm of n. Okay, so that's our problem so far. We've at least removed the -1 portion when we've taken the absolute value of the nth terms. Now we have to test 1 over n square root natural log of n from convergence divergence. I would see a good test for this. For comparison test, we'd have to take, say, a sub n, which is defined to be 1 over n root the logarithm of n, and we have to estimate somehow. This looks like a tough estimate, personally. I wouldn't see a good thing to do to start it off.
If you have the natural log of n with an exponent, can you consider it a p-series less than 1?
Not quite. The natural logarithm itself is not an exponent, sadly. That's really a good point, because if it was something like, say, this, if it was just this altogether, for example, that would be a p-series. and the p would be something like 3/2. But once we threw in the natural log or other functions on that, then sadly it's been messed up a little bit too much. So if we want to try for the comparison test, let's use this nice flow chart since we're thinking about using this on the exam. We would first consider possibly the test for divergence. But if we let n get arbitrarily large towards infinity, this whole thing would converge to 0, so that test would fail. Then it's definitely not a p-series. I mean, it's close. Ditch the natural log, and it is. It's not geometric simply because n does not appear as an exponent, so it cannot be geometric. It is alternating, but we took the absolute value because we're doing step 1, so it's not alternating anymore. Telescoping is very, very particular type of series. We've looked at one in the section 11.2, and they're kind of unusual things to have. So the telescoping series isn't something that's going to be emphasized as much on the third exam. So that one can possibly be, I wouldn't delete it, it's still important, but I would probably put a note to myself that we're not going to cover that one. Then Taylor series is coming up. In the comparison test, the trouble is we have to decide if it converges or diverges and make an estimate. And the estimates involving the root and the natural log, that could require a lot of ingenuity. I'm not too sure what to do. While we're thinking about it, the limit comparison test is just as nasty because you have to come up with something like this. So I'm not sure what to compare that to. So that takes us to the ratio and the root tests, which we haven't quite gotten to yet. All that's left is integral test. But if this was exam 3, I would still probably not use it because there will be one problem on exam 3 written for the integral test in mind. Instructions will say, use the integral test on that particular one. So I would only use the integral test if that's what the instructions reflected. But on this problem, it looks like that's what we need. Let's try to test it with the integral test, which makes it a bit of a review. But not really in the sense that this is how these tests kind of work. They tend to pull other tests into them. So with the integral test, the star of this test is we have to come up with a continuous function. So we let f of x be equal to, let's go over here, since this is the thing we're testing. We can make it be 1 over x square root of the natural log of x. Okay, and I think there's a bit of a mistake here. This should have started at 2. Oh dear, that's a mistake that covers the entire chalkboard. We have to start at 2 because the natural logarithm of 1 is in fact 0. So we can't start with index n is 1 on this problem. We'll start with 2, so we don't take the square root of 0 in the denominator. So let's let that be our function. Then f is continuous on 2 to infinity because we changed the problem to make it continuous. Not continuous on 1 to infinity, so that previous version, the integral test cannot be applied. Well, it could because if only finitely many terms in a series affects convergence divergence, but we would have to change something. So it's definitely continuous on 2 to infinity. Does that make sense to folks so far? Okay, this is one that I'll leave. Well, let's go to this one next, maybe. F is positive on 2 to infinity. By that we mean if you take a look at f of x, it'll come out as something positive on that domain. Yeah, question?
Do you want us to demonstrate this? Like also demonstrate that it's decreasing?
Oh, that's what I was going to get to, yeah. For the first two, you should be able to just inspect and say it, and that would be just fine. For the last one,
So you have to take the derivative?
yeah, we want to determine if all that's decreasing, but that just depends. We could take the derivative. Anyone see another way to reason 1 over x natural log x should be decreasing on 2 to infinity?
Yeah, because if you have the limit, it's getting closer.
Yeah, in the limit, everything's going closer to 0. I mean, that still could be bad, right? Because things could do this, for example. They could oscillate in this way, and the limit could approach 0. But we also know that the function's always positive. The limit is 0, so that forces it to be decreasing. That's probably a decent argument that I would go for on the exam. Yeah, go ahead.
Could you just show like 3 terms if you wanted to too, to show that it's decreasing? Or
That would be decent, I'd say. The trouble is that things can sometimes confuse us. The first few terms could be decreasing. Then it could start to do things like this where it alternates. So as long as it's clear that there's no crazy thing happening with the sequence where the terms could possibly flip.
Like a sine function or something?
Exactly, yeah. Then I would say that's a decent way to do it as well.
Okay.
So let's go with this last bit. F is also decreasing on 2 to infinity since it's positive there. By there I mean the domain from 2 to infinity. And the limit as n goes, well not n, it's x now, as x goes to infinity of f of x is 0. Since we have things that are just growing arbitrarily without bound and a constant in the numerator. So that establishes decreasing. Any questions then with those 3 portions? Okay, then the integral test can finally begin. In the integral test, we need to look at a particular definite integral. We probably have to do it way over here. So next step, we take a look at the definite integral from 1 to infinity of f of x dx. So we need to determine if this type 1 improper integral converges or diverges. So this is now going to be equal to the limit as n goes to, let's not do n, but how about t goes to infinity? I get used to n's after a while in this chapter. This is now the definite integral from 1 to t, but the value of t will increase. And f of x was 1 over x times the square root of the natural log of x dx. So we have to work out that limit. Any questions about that so far?
Should your lower bound of the integral be 2?
Oh, thanks. It ought to be 2 as well. You get so used to the 1s that it's sometimes easy to lose sight of that. Thanks for spotting it. That one would have been a horrible integral. So let's go from 2 to infinity and not worry about the discontinuity, just the fact that t is going to infinity. Other questions or comments so far? Okay, thanks for spotting that. Next, we need to solve this by making some kind of integration technique. Anyone see the technique to use on this thing?
So x's cancel natural log and a natural log.
Yeah, exactly. If we let u be, you're saying natural log x?
Natural log x.
Gotcha. If u is natural log x, then yeah, du would be 1 over x dx. And that would work on this one. Does that look all right to folks so far? Okay, so let's use that as our substitution. Then this would become the limit as t goes off to infinity. Then if we throw 2 inside here, this would be the natural log of 2. And if we throw t inside of here, this would be the natural log of t. Or you could undo the substitution as always. That's always a decent step. The 1 over x dx gets replaced with du. So this and this becomes du itself. And all we have is 1 over the square root of the natural log. But that becomes 1 over the square root of u. So we're on our way. That look all right to folks so far? Okay, and when I look at 1 over root u, I have a psychological need personally to think of that as u to the power of negative 1/2, just so I get the direction right in the antiderivative for the very next step. So now we can say that this is equal to the limit as t is approaching infinity. Here I'm thinking of this as u to the power of negative 1/2. So in the antiderivative, I'll add 2 over 2 to this to get u to the power of positive 1/2 multiplied by the reciprocal to get a 2, and we are evaluating from natural log of 2 up to the natural log of t. So that's what that would look like right before the evaluation. Any questions with the antiderivative so far? Okay, I changed my limits of integration, so I'll leave it as a variable u. If you kept it as going from 2 to t, here to here, just make sure you replace u with a natural log x. Then, from then on, our work will look identical. I'll have 2 times the limit as t goes to infinity, since the limit of a constant multiple is that constant multiple times the limit. And the evaluation would give me square root of the natural log of t minus, then we'll do it at natural log 2, minus the square root of the natural logarithm of 2. Okay, this could be a problem because if this involved a variable t, it would be an infinity minus infinity, and we may have an indeterminate form. But this time, as t goes into infinity, the natural log approaches infinity, the root of something that's going to infinity still goes to infinity, and the measly constant has no effect. So this is diverging to infinity, or divergent. Okay, so we have completed the integral test, really for the sake of review, which means we can come back over here and say that the series n goes from 2 to infinity of absolute value of a sub n. What's the conclusion for that series?
It's conditional.
Not quite.
This is divergent, right?
Yeah, so this one itself is divergent, which means this cannot be absolutely convergent, and our next step will be to show it's conditionally. But so far, this one with the absolute values that we started investigating diverges. And I'll add this for emphasis. We already said it's divergent, and we said what the test was that we're going to use, so we don't have to repeat it. It diverges, and so the original series, as n goes from 2 to infinity of a sub n, so no absolute values, is not absolutely convergent. And that was our first step. We showed that something is not absolutely convergent. Now there's two possibilities. It's either going to converge conditionally, which is better since that's what the instructions were saying, or maybe the instructions were flawed and it diverges. So we're down to two possibilities in our trichotomy. Any questions to that step? Okay, so step 1 was to show that it does not converge absolutely. Step 2 is to show that the original thing is actually convergent. So next, we'll show as n goes from 2 to infinity, the summation of a sub n converges. So we have to pick a test for that, which means we're now just looking at this series, so the form that this takes. So what kind of a series did we say that that ought to be? Let's go back to the flow chart. So at the very top, test for divergence once again still fails because the limit as n goes to infinity of all of that is 0, sadly. The constant in the numerator does oscillate. It's not exactly constant, but the denominator grows arbitrarily large without bound. So the test for divergence is out. What's the next most promising test on this flow chart then?
Is it the alternating series?
Yeah, we still have our alternating portion. When we did this to show it's not absolutely convergent, we ditched the alternating feature of the series by going to the absolute value of the nth term. But now this is still in play, and so it's an alternating series. And that's the test we ought to use. If we have an alternating series, not always, because we're about to get a new test, but very often, at least so far, the alternating series test is the best to go. So we'll show that this converges. We'll say we're going to use the alternating series test. And the alternating series test, the most important feature is the b sub n. Let b sub n be equal to, often that's something that we're using in a comparison test, but in the alternating series test it has a different meaning. The b sub n is always equal to this stuff. 1 over n times the square root of natural log n. In other words, the b sub n is the portion of the series that is always positive, is not alternating. So we take that and set b sub n equal to 1 over back to n times the natural log of n in the square root. Then there's two things we have to establish. We need to show, well, we know first that the sequence b sub n is decreasing. We definitely know that this time. It's not something that we would have to re-show. Does that make sense why? Essentially, we have already shown it once, right? Well, if we show that the function 1 over x natural log x is decreasing, which we did down here in the hypotheses, then the sequence itself has to be decreasing as well, since the curve that the function produces is essentially the guide rails for the points that the sequence produces. So this is decreasing.
Which means the limit is also going to 0, which is a conditional.
Exactly, yeah. So the last part in this alternating series test is to take the limit as n goes to infinity of b sub n, but that would be the limit of all of this. Like you said, that limit is 0, and root natural log of n comes out at 0, and that's actually good in this test. I mean, we've been programming ourselves to say if the limit is equal to 0 in the test for divergence, then that's a yes for the limit is 0. We have to read that right. That whole test fails, and the arrow is telling us to try something else. That test did not work. If the limit is not 0, which is a no, then we have divergence. But in the alternating series test, we have bn plus 1 is less than or equal to bn. That's the decreasing. The limit is equal to 0, so both of those worked. That's a yes. And our conclusion is convergence. So we can say the series converges. Any questions with that so far?
So if it's an alternating function,
Mm-hmm.
or series rather, we could always just use the alternating series test, but our new test is differentiating with whether or not it's conditional.
Exactly, yeah. And so that was the one feature of the instructions to really watch out for, especially in an exam situation. The instructions wasn't saying test for divergence, convergence. It was show the whole thing is actually conditionally convergence. So that's why we had to use 2 tests to get through it. Other questions about that so far? There's still one thing missing. Anyone see the last comment to throw on there that we haven't quite done so far?
Say that's conditional.
Yeah, so we need our end conclusion. The whole punchline to the entire chalkboard so far is the following. So our conclusion is that the series, as n goes from 2 to infinity, of a sub n, is conditionally convergent. So this is yet another very, very weird series. And if we rearrange the terms of the series, you can make it converge to whatever you want. That sounds really, really strange. But that's, again, part of the optional discussion in this section. But any questions at all with that problem then, so far? Okay, so we have a couple more tests and about 9 minutes. Let's maybe introduce the ratio test, do a quick problem. Then we'll come back to the ratio and root tests, as well as the 11.7 problems of trying to put it all together for one review section. Does that sound all right to folks so far? Okay, so for the interest of time, this is the next test we're going to look at, the ratio test. The ratio test is a very, very fancy test. It does have some downfalls in that it can take a while to use this test when there's other readily available tests. But the ratio test and its companion, the root tests, are extremely powerful because they can be applied in many situations. We just don't want to apply it every single time it can work because that could be more work. The proof of this is based on the geometric series, and the geometric series has a condition of convergence when something is less than 1, and here we look at a limit. It also has a condition of divergence whenever the limit is greater than 1 or is infinity. And we have one extra problem. This test just does not work because of a defect in the way it was proved. When a particular limit comes out to 1, then the ratio test has failed, and we have to pick something else. So let's try out this entire test with a whole new series. For this kind of problem, it'll simply say to determine the convergence or divergence of whatever the given series is. So now we don't have to do a bunch of tests to see if something's conditionally convergent. We're not even trying to show if something's absolutely convergent. We're just doing same kinds of things that we've been doing all along. And for our first problem, let's take a look at the summation as n goes from 1 to infinity of -1 to the power of n times n factorial divided by 3 to the power of n. So the n factorial is definitely a new feature in this problem. And a lot of times when you see factorials, it means the ratio test is probably a good way to go. So let's start off by doing the ratio test. So by this factorial symbol, we will use the ratio test. It's called the ratio test because we're going to take a particular kind of limit that involves a ratio of the nth term plus 1 with the nth term. So first we have to look at what is an plus 1. So if this is the form for the a sub n, then an plus 1 would be an n plus 1 factorial divided by 3 to the power of n plus 1. Because an plus 1 just simply means put n plus 1 everywhere where the index n has occurred. So I've dropped it in these two places. Oh, and don't forget, there's also a -1 to the power of n plus 1 as well. Okay, then we just have to get comfortable with factorials because they're all over this problem. Just for a quick rundown, if you write 3 factorial, it means you're computing 3 times 2 times 1. If you compute n factorial, then the formula for that would be n times n minus 1 times n minus 2, and depending on how large n is, this could take quite a while to write out. So we put ... to say and so on, until you get to 3, 2 times 1. So that's essentially what the factorials look like. They grow very, very rapidly, faster than exponential functions evaluated at the integers. And up here, if you have an n plus 1 factorial, we can simplify that as well. Because if n factorial is n times n minus 1 times n minus 2, then that pattern would continue. With n plus 1 factorial, we start with n plus 1, multiply by n, multiply by n minus 1, really the same pattern as above. Then we descend all the way to the last integers, 3 times 2 times 1. But that means n plus 1 factorial could also be expressed in a new way. Let me see, that's the right angle there. Because n times n minus 1 times, oh, there should have been a ... there. Must have ran out of space. N times n minus 1 times 3 times 2 times 1. All that is really just n factorial itself. So n plus 1 factorial could be rewritten as n plus 1 times n factorial itself. And that's really the major tricks to getting through a problem like this one. Any questions about the factorial stuff so far? Okay, we really haven't done much with factorial because this is the first time we have a test that can handle it in a nice, reasonable way without strange estimates. So this now can be rewritten as -1 to the power of n plus 1 factorial. I would always write that as an n plus 1 times n factorial because I would always be expecting a cancellation in the ratio test. Then the denominator is 3n plus 1, but I'm expecting another cancellation, so it's also handy to factor it in this way by exponent laws, 3 to the 1 times 3 to the n. So once we have a handle on an plus 1, then the test can proceed. Any questions so far? Okay, the reason this test is really, really powerful is notice that there is no hypotheses really for this. It just says consider the series. We don't have to have a continuous function that's continuous, decreasing, and positive on a specific domain. The terms of the series can be positive, negative, they can alternate, they don't have to alternate. This works on everything when it works. So now we're going to take a look at this limit right here. So the limit, as n goes to infinity, of a sub n plus 1 divided by a sub n. And that order is important, or else we'd have to change the order of the conclusions here. So make sure an plus 1 is always in the numerator in that limit. This then becomes the limit, as n goes to infinity, of the absolute value of first I'll do an plus 1, which is way over here. So negative 1 to the power of n plus 1, n plus 1 times n factorial, divided by 3, times 3 to the n. So that takes care of an plus 1. Does that look all right to that step? Okay, then we're dividing by a sub n, which means we should just multiply by the reciprocal of that, or else we'll run out of time trying to write down everything. So I'm going to take the reciprocal of a sub n, that's our a sub n there, and we'll get 3 to the n, divide by negative 1 to the power of n times n factorial. All of that in absolute values.
So it's n plus 1 over 3.
So n plus 1, say, cancels? Or
No, that's what you're left with, right?
yeah, exactly. So first, really, all that stuff is just dead because of absolute values, right? Then next, the 3n cancels, and also the n factorial cancels. So yeah, it's just all of that left. N plus 1 divided by 3 in the limit. Any questions with those cancellations so far?
And that's why we do all this, we can cancel this.
Exactly, yeah. So it really pays off to take a look at the n plus 1 term and just simplify it as much as you can, expand it in the right ways because of expecting a cancellation. Then this whole thing becomes, I mean, you could write this as the limit as n goes to infinity of n plus 1 divided by 3, but the whole thing is infinity itself because we have something growing without bound in the numerator and a constant denominator. So that means if we've got infinity, that's this possibility here in case 2. And the conclusion would be by the ratio test, which we've already indicated, it diverges. What is going to be truly awful is when this comes out to exactly 1, and it will definitely happen. It's just designed to happen when we look at power series, Taylor series, and Maclaurin series. When this comes out as a 1, we have to go back to all of these other tests that we've looked at. So that's the reason, even though this is a very, very powerful test, all the remaining tests are still of utmost importance because this test will fail in certain situations. But if you have questions, feel free to stick around. It looks like that's about the end of the material we have. When we come back, we'll do a couple more ratio problems and root problems. Then we'll start summarizing in section 11.7 all of the tests.